Hey everybody, Dr. Phil here. So this is a quick video on project analysis and evaluation. The first thing we're going to talk about in this video is evaluating NPV estimates, net present value estimates. Okay. So remember, if we have an NPV that's positive, that's a good sign, right? It means we're at least achieving the hurdle rate. But more than anything, it tells us that we need to take a closer look. So what do we mean by that? So the projected cash flows are not ultimately likely to equal the actual cash flows, right? Because it's in the future and we don't know what's really going to happen in the future. So when we say something like the projected cash flow in year four is 700, what exactly do we mean? So we don't necessarily think it'll actually be 700, but rather if we took all the possible cash flows that could occur in 4 years and average them out, the result would be 700. So this is where we speak to forecasting risk. So this idea of estimation risk, right? It's the possibility that errors in projected cash flows will lead to basically bad decisions. So the source of value answers the question, what is it about this investment that leads to a positive NPV? So this is like the first line of defense against forecasting risk. And the key factors to keep in mind are the degree of competition and potential competition in the market. What I mean by that is who's around now that may forestall us and who potentially could be around in the future. So the first thing to do when investigating a new project is estimate the NPV based on projected cash flows. So the initial set of projections we call those the base case. After completing those, investigate how different assumptions about the future will impact our estimates. So it's kind of like a what if analysis, as it says. So one way to do this is by putting upper and lower bounds on the various components of the project. So the project under consideration costs 200 grand in this example, has a 5-year life and has no salvage value. Depreciation is straight line down to zero. The required return is 12% and the tax rate is 21%. Now, in addition, we have compiled the following information. So you can see the base case here. You can see the lower bound, lowest, you can see a lower amount of sales, and then you see the upper bound, of course, higher sales. We've got the price per unit, we've got the variable cost per unit, and then you can see down here what we would ultimately make. So with this information, we can calculate the base case NPV by first calculating net income. So if we plug in the numbers, sales minus our variable costs, take out our fixed costs, we're going to subtract this non-cash expense depreciation. We have earnings before interest and taxes, also called operating income, 30 grand. Then 21% of the 30,000 taxes is 6,300. And then we have net income of 23,700. Okay. The operating cash flow is 30,000 plus 40,000 because we're not actually paying out that depreciation expense. It's just a non-cash expense. Okay. And then we're minusing the 6,300 in tax because we do have to pay that. So the operating cash flow is actually 63,700. At 12%, a 5-year annuity factor is you can look in your tables for this. Just go to your annuity table. You're looking for the PV. PVA, present value of annuity, 3.6048. So the base case NPV is the 200,000 plus the 63,700, and then times that annuity factor, the 3.6048, and we get 29,624. Now, scenario analysis is the determination of what happens to NPV estimates when we ask what if questions. What if we make less money? What if we make more money? What if expenses are higher than we thought? There's a multitude of questions we could ultimately ask, right? We can consider a number of possible scenarios, but let's start with the worst case and the best case. So these are the numbers we had before, the 5,500 unit sales and the 6,500 unit sales. So we'll now calculate the net income and cash flows for each scenario. So that's kind of what I've done down here. So you can see the base case. We have 23,700 in net income. We have IRR, internal rate of return, of 17.8%. The worst case scenario, we're losing about 18.5 grand. It projects a negative 17.7 internal rate of return. And then for the best case scenario, we're going to do really well, right? 71,495 with a projected IRR of 47.9%. Now, sensitivity analysis, just think of this as, what's going to happen to your NPV when you just change one variable at a time. You got to be careful changing more than one variable because you need to know if I change this one, what does that do to my numbers, right? If you change too much at once, you may lose, okay, well, what's causing what, in a sense. Returning to our base case, for every item except unit sales, we can calculate cash flow and NPV using the largest and smallest unit sales figures. So as you can see here, we've got net income for the base case of 6,000. But again, the worst case was 55. Best case scenario was 65. And then we've got the cash flow that would be coming in. We've got our NPVs from before, and then we've got the internal rate of return numbers listed out. So we can freeze everything except fixed costs and repeat the analysis. And that's exactly what we're doing below. So as you can see, base case, the IRR doesn't change. It's still 17.8. If you look at the worst case, the IRR has actually improved slightly, 15.1 for the worst case. And then for the best case, it's actually gone down slightly, right, from 23.2 down to 20.5. So this just kind of illustrates this idea of, if you just mess with like one variable, in this case, fixed costs are what we adjusted, then you can kind of see the impact that has on cash flow and also on the NPV and the resultant internal rate of return. So the results of sensitivity analysis for unit sales we could also illustrate this graphically, right? So we're going to put NPV, a net present value, on the vertical axis, and we're going to put sales on the horizontal. So when we plot, if you look at these 3 points, when we plot the combinations of unit sales versus NPV, all possible combinations fall on a straight line. But the steeper the resulting line, the greater the sensitivity of estimated NPV to changes in projected value of the variable being investigated. So it's like saying like the gradient is higher, if you will, right? The slope is higher, so thus there is increased sensitivity. Now, break-even analysis is popular and is commonly used a tool for analyzing the relationship between sales volume and profitability. The sales volume is usually analyzed more closely than other variables for obvious reasons. Companies care a lot about what they sell, how much money they're making. Variable costs change when the quantity of output changes, and they are zero when production is zero. Think about it, because if you don't produce anything, you don't have any variable cost. Think about the name variable, they vary, right? The relationship between total variable cost VC, cost per unit of output V, think about volume, and total quantity of output Q, quantity can be written as VC variable cost or total variable cost equals Q, total quantity of output, times V, the cost per unit of output. So let's, as an example, let's suppose variable cost V are $2 per unit. If the total output Q is 1,000 units, what will total variable cost be? So we just plug in your numbers, right? So Q is, the quantity is 1,000, the variable cost per unit is 2, so we get 2,000. So simple enough. And fixed costs, on the other hand, do not change when the quantity of output changes during a particular time period. So for example, like a lease payment, that has whatever you have to pay for the lease payment has no bearing on how much you produce. So the total costs, TC, for a given level of output are the sum of variable cost VC and fixed cost. So we could say that total cost TC equals VC variable cost plus FC fixed cost. So we could say equals V times Q plus FC. So if variable costs are $3 a unit and fixed costs are 8,000 a year, our total cost would just be 3 times the Q plus the 8,000. So then, by way of example, if we produce 6,000 units, then just plug in Q as 6,000. So as you see over here, 3 times 6,000 plus the 8,000 would give us the 26,000. And you can kind of see here, there's just some different scenarios. What happens if you produce 1,000 units, if you produce 5,000 units, and if you produce 10,000? Notice what's happening to the variable costs, they're increasing, and notice that the fixed costs are not increasing. Now, by plotting the points from the table in the previous slide, we see that the relationship between quantity produced and total costs is given by a straight line. Notice that the total costs equal fixed costs when sales are zero, because at that point, when sales are zero, right here on the y-axis, think about the y-intercept, you have no sales, right? So the only costs you're paying at that point are your fixed costs, like the rent, the lease, etc. Now, beyond that point, every 1 unit increase in production leads to a $3 increase in total cost. So the marginal or incremental cost of producing 1 more unit is $3, which represents, of course, that variable cost. And if that 3 went to like 4, then the gradient would, of course, become a little steeper, and vice versa. All right, so let's take a look at average cost versus marginal cost. So let's look at an example. Suppose the Bloom Corporation has a variable cost per pencil of 55 cents. The lease payment on the production facility runs $5,000 a month. If they're going to make 100,000 pencils a year, what are the total costs of production? What is the average cost per pencil? So we know the fixed cost of $5,000 a month, or times 12, $60,000 a year. The variable cost is 0.55 per pencil, 55 cents. So the total cost for the year, assuming that they produce 100,000, just plug in your numbers, right? So 0.55 for V, 100,000 for Q, and then 60,000 for the fixed cost equals 115,000. So the average cost per pencil, we would just take the 115 total cost, divide it by the number of pencils. They said they were producing 100,000 pencils per year, and then we get $1.15 per pencil. Now, suppose that Bloom has received a special one-shot order, so like a one-time order, 5,000 pencils. Bloom has sufficient capacity to manufacture the 5,000 pencils on top of the 100,000 already produced. So no additional fixed costs will be incurred. Also, there will be no effect on existing orders. If Bloom can get 75 cents per pencil for this order, the question is, should the order be accepted? And here is what it comes down to. If it's going to cost them 55 cents to make another pencil, anything that Bloom can get for this pencil over that 55% incremental cost contributes in a positive way towards covering their fixed cost, right? By doing the special order, their fixed costs don't change, so they don't really worry about those. They're just worrying about the variable cost per pencil, the 55 cents. So the 75-cent marginal or incremental revenue exceeds the 55-cent marginal cost, thus Bloom should take the order. But as I said, the fixed cost of 60 grand, it's really irrelevant to the decision because it's effectively sunk, right? At least for that period. You're going to have to pay it either way. Now, in the same way, the fact that the average cost is $1.15 is irrelevant because this average reflects the fixed cost. So long as they produce the extra 5,000 pencils and it doesn't cost them anything above that 55 cents, then they really should, frankly, anything they get offered over 55 cents, they should, like 56 cents, as silly as it sounds, they should still take it. All right, let's now look at operating cash flow, sales volume, and break even. So this company, Wetway Sailboat Corporation, is considering whether to launch its new Imago class sailboat. The selling price will be $40,000 a boat, variable cost will be $20,000 per boat, and fixed cost will be $500,000 per year. The total investment needed to undertake the project is $3.5 million, which will be depreciated straight line to zero over the 5-year life of the equipment. The salvage value is zero, and there are no working capital consequences. That's great. The required return is 20%. So Wetway projects total sales for the 5 years at 425 boats, or about 85 boats per year. Ignoring taxes, should this project be launched. So operating cash flow at 85 boats per year is, the formula we're going to use is operating cash flow equals EBIT plus depreciation minus taxes. And remember, EBIT is earnings before interest and taxes. Okay, so we could say sales minus the variable cost, VC, minus the fixed cost, FC, minus the depreciation, plus it's the depreciation back in equals, minus zero. So plug in your numbers, right? 85 times the 40,000, subtract the 20,000, and then just subtract the fixed cost of 500,000, and we get 1.2 million per year. At 20%, the 5-year annuity factor, look at those look at your PVA, present value of annuity table. So at 20%, the 5-year annuity factor is 2.9906, and so thus the net present value is, again, plug in your numbers, 3.5. Put in the negative 3.5, right? Because that's what you have to spend now, and then add the 1.2, and then multiply it by the present value factor. So if you simplify that out, we get a net present value of 88,735. So it's positive, and we're obviously beating our return of 20%. Before fixed costs and depreciation are considered, Wetway generates 40,000 minus 20,000, which is of course the 20,000 per boat. So that's the revenue minus the variable cost. We knew that they were doing this over 5 years, so we take the depreciation of 3.5 million, divide it by 5 years. There is your 700,000 per year. Fixed cost and depreciation together total 1.2 million. So Wetway needs to sell basically 1.2 million divided by 20,000 is 60 boats per year in order to break even on an accounting basis. To calculate Wetway's cash flow in this sense, we note that if 60 boats are sold, net income will be exactly zero. Now remember, operating cash flow for a project can be written as net income plus depreciation. So that's like it says the bottom up, like starting at the bottom, working your way up. Operating cash flow is equal to the depreciation, or 700,000. Now ignoring taxes, the project's operating cash flow, or OCF, can be written as EBIT, again, earnings before interest and taxes, plus depreciation. So as you can see, we have a formula here. The one great thing about this is there's always a formula, we just plug in the numbers. So now for the Wetway Sailboat project, the general relationship in thousands between operating cash flow and sales volume is, let's plug in the numbers, P 40, V 20. Remember, these are in thousands because if they were selling the boat for 40 grand, the variable costs were 20 grand, multiplied by the quantity, and then minus 500,000 for the fixed cost. So minus 500 plus the 20 times the Q. So the relationship between operating cash flow and sales volume is just simply given by a straight line with a slope of 20, think about the gradient, and a y-intercept of negative 500. That, of course, represents your fixed costs. So if we play around with these values, we can kind of see what happens. If we don't sell any, we have to pay the 500. The more we sell, the more the variable costs go up. So obviously, but the more money we make, so the higher the operating cash flow becomes. And then we've also plotted these down here all the way up to, you can see here, we have our break-even point. So we've shown the relationship between operating cash flow and sales volume, which are ignoring taxes, which is operating cash flow equals P minus V in parentheses times the quantity minus the fixed cost. So if we rearrange this and solve for Q, the result tells us what sales volume Q is necessary to achieve any particular OCF. So looking at the graph on the slide before, let's say the operating cash flow is equal to depreciation, which we denote D, term D. Recall the situation corresponds to our break-even point on an accounting basis. To find the sales volume, substitute the 700 depreciation amount for OCF in our general expression. So as you can see, I plugged in down here. So Q equals FC, fixed cost, there's your 500, plus the OCF of 700, and then over P minus V, which of course was 20. Think about the 40,000 minus 20,000, the price and variable cost, and we get 60. All right, cash break even. So this is the sales level that results in a zero operating cash flow, and it's calculated as follows. So the formula is Q equals FC over 0 in parentheses over P minus V on the denominator, also in parentheses. So very simple, right? 500 divided by 20 is 25. So what we're saying there is the Wetway must sell 25 boats in order to cover the 500 in fixed cost. Now the financial break-even is the sales level that results in a zero net present value. So to determine what operating cash flow must be for the NPV to be zero, and we'll just use that amount to determine the sales volume. Now, remember, the company wanted a 20% return on its 3,500, of course, in thousands investment. So how many sailboats does Wetway have to sell to break even once we account for the 20% per year opportunity cost? So the 5-year annuity factor at 20% is, again, look in your table, 2.9906. Operating cash flow is 3,500. So we're just going to take 3,500 equals OCF times the PVA, present value of annuity factor. Just rearrange it, and we get 1,170. So now if we plug that into the OCF for the equation for sales volume, we get 83. So we're basically saying that it's the quantity that they must sell is 83.5 in order to break even from a financial standpoint. Okay, another term I wanted to make sure we cover just real quick, operating leverage. So think of operating leverage as the degree to which a firm or project relies on fixed costs. So a firm with low operating leverage will have low fixed costs compared to a firm with high operating leverage. Projects with a relatively heavy investment in plant and equipment will typically have a high degree of operating leverage, and these projects are said to be capitally intensive. So it just means that's a fancy way of saying they take a lot of money. Operating leverage has important implications for project evaluation. Fixed costs act as a lever in the sense that a small percentage change in operating revenue can be magnified into a large percent change in operating cash flow and NPV, net present value. The higher the degree of operating leverage, the greater is the potential danger from forecasting risk. So let's take a look at how to measure operating leverage. So the DOL, the degree of operating leverage, is the percent change in operating cash flow relative to the percent change in quantity sold. And it is defined such that the percent change in OCF equals the DOL, degree of operating leverage, times percent change in quantity. So based on the relationship between OCF and Q, we can write the DOL as 1 plus the fixed costs divided by operating cash flow. So going back to the Wetway example, we know the fixed costs were 500, the price minus the variable costs were 20, so the OCF was just 500 plus 20, and then times Q. So let's say that Q is currently 50 boats. So at this level of output, OCF is minus the 500 for the fixed costs, plus the 1,000 equals the 500. If we increase Q by 1 unit to 51, then the percent change in Q is 51 minus 50. Over 50 equals 0.02, or we could just say 2%. If OCF rises to 520, a change of PV equals 20. So the change in OCF, of course, now has now gone up to 4%. So it's kind of one of these things where if you want to, you can just kind of play around with it and just, do a little bit of a scenario analysis, a little bit of what if analysis. So we can verify that the degree of operating leverage DOL is exactly 2 by noting that we know the DOL equals, like we said, 1 plus FC over OCF. So 1 plus the 500 fixed costs over the operating cash flow of 500. So of course we get what? 500 over 500 is of course 1, so just 1 plus 1. There's your 2. Well, let's say suppose Q rises from 50 to 75, a 50% increase. With DOL equal to 2, operating cash flow should increase by 100%, or exactly double. So let's make sure it does. So at a Q, a quantity of 75, OCF is going to be minus the 500 fixed cost, plus the 20, think of that as like contribution margin, times the 75, and there it is, we get the 1,000. Now notice that operating leverage declines as output Q rises. So for example, at an output level of 75, we have the DOL equals 1 plus the 500 over the 1,000, and now of course we've increased it to 1.5. So let's look at another example of operating leverage. So the Sasha Corp currently sells gourmet dog food for $1.20 a can. The variable cost is 80 cents per can, and the packaging and marketing operations have fixed costs of 360 grand a year. Depreciation is 60,000 a year. What is the accounting break even? Ignoring taxes, what will be the increase in operating cash flow if the quantity sold rises to 10% above the break even point? So the accounting break even is 420,000 over 0.4, and then that's going to give us 1,050,000 cans. As we know, the operating cash flow is equal to the 60,000 depreciation at this level of production. So thus the operating leverage is just the 1 plus the 360. That of course are your fixed costs, and then just divide it by the 60,000 and we get a DOL of 7. So given this, a 10% increase in the number of cans of dog food will increase operating cash flow by a substantial 70%. So there's the idea of your lever, right? You increase sales by 10%, you increase your cash flow by operating cash flow by 70%. Now to check this answer, we know that if sales rise by 10%, then the quantity sold will rise to 1,050,000 times 1.1. There's factoring in the 10%, equals 1,155,000. Ignoring taxes, the operating cash flow will be the 1,155,000 times 0.4 minus the 360 is going to give us the 102,000. Now, compared to the 60,000 cash flow we had, this actually turns out to be exactly 70% more. We take the 102 over the 60 and we get the 1.7. So just think of that as a way to verify it, as a way to confirm it. So at a quantity of 85 boats, the degree of operating leverage for the sailboat project under the original scenario is, so we have the DOL equals 1 plus FC over OCF. So therefore it was 1 plus the fixed cost of 500 over the operating cash flow of 1,200 equals, and there's your 1.42. Now remember, the NPV at a sales level of 85 boats was 88,735, and the accounting break even was 60 boats. So Wetway could, in theory, subcontract production of the boat hull assemblies, which would decrease the necessary investment to 3.2 million, would also decrease the fixed operating cost to 180,000, and increase the variable cost to 25,000 per boat. If we do that, then here's what's going to happen. The net present value at 20% at 85 units would be 74,720, still positive, so that's good. The accounting break even is 55 boats, and the degree of operating leverage is 1.16. So this option results in a slightly lower estimated net present value, and the accounting break even falls from 60 to 255 boats from 60 boats. So this is something that they could consider. If they're looking at maybe getting out some of those fixed costs, it might not be a bad idea for them. Okay, as always, thank you for watching, and I will see you in another video. Take care.